This content is produced by PASS, the CSLB, an independent audio-first study companion for busy California B general candidates. I build these lessons from official CSLB study guide topics and reputable source-backed California materials so you can study on the go. This is exam prep reinforcement, not legal, professional, engineering, or job-specific advice. Exam content is set by PSI and the CSLB and may change, so always verify current requirements against official CSLB materials. No exam outcome is guaranteed. Now let's get into it. A condensate drain is a small pipe, but the general building supervision problem is much larger than the pipe. The key question is what happens when that normal drain stops carrying water while the equipment sits above drywall, insulation, flooring, or another finish that can be damaged. A sound installation does not depend on one hidden path working forever. It gives normal condensate a proper route, keeps that route serviceable, separates it correctly from the plumbing drainage system, and adds a second layer of protection where an overflow could damage the building. I want you to remember the central chain this way. Drain it, separate it, back it up, make failure visible, and leave safe access for service. That is the general building contractor's view of this topic. I'm not asking you to design refrigeration capacity or engineer the equipment. I am asking you to supervise the places where heating, ventilation, and air conditioning work intersects with plumbing, framing, electrical work, finished surfaces, and inspection readiness. Imagine a crew installs an air handler in an attic above a finished bedroom. The primary drain looks clean on rough inspection. Months later, that line becomes blocked. If there is no effective secondary protection, the first visible sign may be damage below the unit. If there is a properly coordinated overflow switch or secondary pan with an observable drain, the failure creates a warning or stops the equipment before the same condition silently reaches finished work. That difference is the heart of condensate coordination. The primary drain handles the water produced during normal operation. California requirements call for condensate from air cooling coils to be collected and discharged to an approved plumbing fixture or approved disposal area. That statement sounds basic, but the field details determine whether gravity can actually move the water and whether the line can still be maintained after the project is closed up. The horizontal condensate waste pipe needs a minimum slope of 1/8 of an inch per foot, which is 1%. That is a minimum, not permission, to let the pipe rise, flatten out, or sag between supports. On a long run, framing, ductwork, piping, and ceiling elevations can all compete for the same space. I want the drain route settled early enough that the installer can maintain continuous fall instead of creating a low spot after every other trade has already claimed the chase. For equipment up to 20 tons of refrigeration, the minimum condensate pipe diameter is 3/4 of an inch. That range covers the residential and light commercial equipment a general building contractor commonly coordinates. The practical inspection point is simple. A small, flexible tube or an undersized improvised line is not a substitute for the required drain size. The drain also needs an accessible cleanout that allows a blockage to be cleared without cutting the pipe. This is a serviceability requirement, not a decorative fitting. Once drywall, insulation, or equipment platforms surround the installation, a technician should not have to cut and rebuild the drain, merely to clear ordinary blockage. I put the primary requirements together in one reference table because they work as a system. The normal drain needs an approved destination, at least 1/8 of an inch of fall per foot, a minimum diameter of 3/4 of an inch through 20 tons, an indirect connection when it enters a drainage system, and a cleanout that works without cutting. The required air gap dimension belongs in that same inspection picture, and I will explain it next. A helpful field check is to start at the unit and follow the entire route rather than inspecting one fitting at a time. I look for a clear collection point, continuous fall, access to the cleanout, and a termination that has not been hidden by later work. A drain can look neat near the equipment and still fail the basic coordination test at the far end. When condensate discharges into a building drainage system, it must do so through an indirect waste connection, using an air gap or an air break. The common mistake is treating condensate as harmless water and gluing its pipe directly into a sanitary fitting, standpipe, or tailpiece. That creates a direct connection, which is not the required arrangement. An air gap is the clearest physical separation. For the required drainage air gap, the vertical distance is at least 1 inch from the lowest point of the discharge pipe to the flood level rim of the receptor. The water leaves the condensate pipe, passes through open air, and then enters the receiving fixture. The two systems are not hard connected. An air break is also an indirect connection, but the discharge pipe may terminate below the receptor's flood level rim while remaining above the trap seal. The exact physical arrangement differs from an air gap, yet the important distinction for supervision is the same. Neither method creates a direct sealed connection from the mechanical equipment into the sanitary drainage piping. Suppose an installer runs a 3/4 inch condensate line down a wall and solvent welds it into a laundry stand pipe. The line may appear secure and leak-free, but the connection method is the defect. The correction is not a better bead of cement. The termination must be reworked as an approved indirect connection at an appropriate receptor. The central cause and effect is straightforward. A direct connection gives the drainage system a continuous physical path back toward the mechanical equipment. An air gap breaks that path with open space. I use the word separate because it keeps the decision clear. The condensate must be allowed to discharge, but the mechanical drain and sanitary drainage system cannot become one continuous sealed pipe. That plumbing detail has to be coordinated before walls close. The heating and air conditioning installer controls the condensate route, while the plumbing work provides the appropriate receptor and drainage conditions. The general building contractor has to make sure those two scopes meet correctly, instead of leaving each subcontractor to assume the other one finished the connection. Secondary protection follows what I call the damage rule. If the equipment is located where condensate overflow can cause damage to the building, an additional protection method is required. The requirement is tied to the consequence of overflow, not simply to the fact that cooling equipment exists. An attic above a finished gypsum board ceiling is the obvious example. A furred space above finished construction can create the same concern. By contrast, the code provides an exception when the only potential damage is to replaceable lay-in ceiling tiles. That exception matters because it keeps you from turning a location-based rule into the false statement that every unit, everywhere, always needs an external secondary pan. The primary pan and the secondary pan are not the same thing. The primary pan is part of the equipment and catches normal condensate from the coil. A secondary pan is a separate, field-installed, watertight and corrosion-resistant pan, placed beneath the equipment as redundant protection. Calling the built-in primary pan the backup misses the entire point. There are several accepted ways to provide the additional protection described in the source material. A water level detecting device can be placed in the primary drain line so a backup shuts the equipment down. A water level detecting device can be placed in the primary drain pan. An auxiliary drain can connect at a higher elevation than the primary outlet. A separate secondary pan can be installed beneath the unit, with its own drain. I put those methods side by side because the method can change while the supervision question stays the same. What detects or receives the overflow? What action follows? And where will the warning become visible? A shutoff device responds by stopping equipment operation. A secondary pan receives water that escapes the normal path. An auxiliary outlet only helps if its route remains separate and functional. When a secondary pan is used, its separate drain pipe must be at least 3/4 of an inch in diameter and must discharge at a readily observed point. Readily observed is not filler language. The secondary line is not supposed to fail quietly into a concealed wall, hidden soffit, buried drain, or other location where occupants are unlikely to notice it. That observable termination turns water into a service signal. If water appears there, the secondary system is telling the occupant that the normal drainage path needs attention. I would rather see a controlled, noticeable drip from a properly located secondary outlet than discover the same water after it has traveled through a ceiling assembly. Consider a hypothetical attic unit with a large metal pan beneath it. The pan is sized and placed correctly, but its drain disappears into a concealed cavity and joins another hidden drain. The metal pan may catch the overflow, yet the coordination is still incomplete because the separate discharge is not readily observed. The contractor has created storage for the problem without creating a useful warning. A float switch presents a different coordination issue. It must be installed and connected so the water level condition actually shuts the equipment down. The general building contractor does not need to redesign the control circuit, but should verify that the required protection is present, accessible, and included in the appropriate trade's testing and inspection scope. Attic condensate protection cannot be separated from attic service access. A beautiful drain installation is not inspection ready if the equipment cannot be reached, removed, illuminated, and serviced from a stable surface. These requirements need framing and electrical decisions long before final mechanical startup. Where attic equipment requires access, the opening must be at least 22 inches by 30 inches, or large enough to remove the largest single component of the appliance, whichever requires more space. The second part prevents the minimum opening from becoming an excuse for trapping a major component permanently in the attic. The passageway from the access opening to the equipment can be no more than 20 feet long. It needs a continuous solid floor at least 24 inches wide. At the service side of the appliance, a solid level work platform, at least 30 inches by 30 inches, is required. I grouped the attic requirements into a checklist because each item belongs to a different coordination conversation. The framer needs the correct opening, walkway, and platform. The equipment layout has to respect the passage length and service side. The electrician needs a permanent 120-volt receptacle and lighting fixture near the equipment, with the light switch at the entrance to the passageway. The switch location is easy to miss. Putting a switch on the unit does not solve the problem of reaching the unit through a dark attic. The light has to be controllable at the passageway entrance, where the person begins the trip to the equipment. Imagine carrying a tool bag through an attic. The access opening is large enough. The light comes on before the first step. The floor is solid and wide enough for the route, and the technician arrives at a level work platform in front of the service side. That single mental walk connects dimensions that otherwise feel like unrelated numbers. The general building contractor's responsibility is coordination. The framing plan must leave the root. The mechanical layout must place the service side where the platform works. The electrical rough-in must include the nearby receptacle, luminaire, and entrance switch. The condensate route must preserve its required slope while the service path remains usable. I use a simple field sequence to catch most condensate coordination defects before concealment. First, I confirm the equipment location and identify whether overflow could damage the building. That decision tells me whether additional protection is required. Next, I trace the primary drain from the equipment to its approved destination. I verify the minimum size, continuous slope, and accessible cleanout. I do not stop at the unit because the worst mistake may be at the receptor. Then I inspect the plumbing interface. If the condensate enters a drainage system, I confirm an indirect connection through an air gap or air break. If an air gap is used, I check the required 1-inch vertical separation above the flood level rim. After that, I inspect the secondary protection. I identify the actual method, not a vague promise that the installer will add something later. If there is a secondary pan, I confirm it sits beneath the equipment, has a separate drain at least 3/4 of an inch in diameter, and terminates where occupants can readily observe discharge. If there is a shutoff device, I make sure testing and responsibility are assigned. Finally, I walk the service path. I check the access opening, the maximum passage length of 20 feet, the solid floor at least 24 inches wide, the platform measuring 30 inches by 30 inches, the light near the equipment, the 120-volt receptacle, and the light switch at the passage entrance. This is where a general building contractor sees the whole job rather than a stack of separate subcontractor tickets. Suppose the framing crew installs a small attic hatch before the mechanical unit is selected. The heating and air conditioning installer later places equipment that cannot pass through that opening. The electrician puts the light switch beside the unit, and the condensate installer routes a flat line across the intended walkway. None of those choices belongs to one isolated trade problem anymore. Together they create demolition, return trips, schedule loss, and failed inspection readiness. The better decision is early coordination. Confirm the equipment footprint and largest removable component before the hatch is framed. Reserve the drain elevation before ducts and plumbing fill the chase. Mark the service side before the platform is built. Put the electrical requirements on the rough-in list instead of discovering them at final. Several confusions are worth clearing up because they produce believable-looking defects. The first is assuming that a line flowing on the day of inspection proves the drainage system is complete. Flow today does not replace minimum slope, required size, a serviceable cleanout, or proper termination. The second is assuming that a secondary pan can share any convenient drain route. The source-backed requirement is a separate drain line that discharges at a readily observed point. Hiding the outlet removes the warning function that makes the secondary route useful. The third is treating a float switch and a secondary pan as identical. Both can serve as additional protection in appropriate configurations, but they respond differently. The switch is intended to stop operation when the water level rises. The pan is intended to receive overflow and route it through its own observable drain. The fourth is placing the attic light switch where the light fixture happens to be. The required coordination point is the entrance to the passageway. Think about the first step into the attic, not the final step at the equipment. The fifth is memorizing dimensions without connecting them to the physical route. I tie 22 inches by 30 inches to getting through the access opening, 20 feet to the maximum travel distance, 24 inches to the solid walking floor, and 30 inches by 30 inches to the level service platform. Each number belongs to a different part of the same trip. The final confusion is overreaching the general building role. I am not teaching you to size refrigeration loads, select coil performance, or modify control design. Based on the published CSLB study outline, this topic fits testable material because it involves trade coordination, defect recognition, field inspection, damage prevention, and safe service access. Here is the complete memory connection. Drain it to an approved place. Give gravity at least 1/8 of an inch per foot. Use pipe with a minimum diameter of 3/4 of an inch through 20 tons. Leave a cleanout that works without cutting. Separate the condensate from sanitary drainage with an indirect connection. Where overflow can damage the building, add secondary protection. If a secondary drain is used, make it separate, at least 3/4 of an inch, and readily observed. In an attic, preserve the access opening, passage, solid floor, work platform, light, receptacle, and entrance switch. The central lesson is not that condensate piping is complicated. It is that one small drainage path sits at the intersection of several trades and several finished surfaces. Good supervision assumes the normal path may eventually need service and makes sure the building has a controlled response when that happens. There is an audio practice quiz for this specific episode, built around condensate drains, secondary pans, overflow protection, indirect waste connections, and attic coordination. It is audio-based. I read the questions aloud, and you answer by tapping, because I know you may be studying while driving, working, or moving between jobs. Go to the description below this video. You will see a link that says Pass the CSLB. Tap it. It will take you straight there. Comment below with any questions about anything I covered. Subscribe so I can help you stay on track through every episode until you get your license. I take that goal seriously, and I'm glad to be part of the work you are putting into it.